Hello, today we are starting electric currents and electricity, which I think is a pretty cool topic. So, what is an electric current? What makes current flow? And many other questions shall be answered. Uh, so, the three big ideas that we're going to be dealing with are current, voltage, and power, and resistance, current, voltage, and resistance. Uh, Electrical power will be important too, but not as important as these three. These are the big three. So an electrical current really is just a flow of electrons around some sort of conducting material. So uh, there's got to be something that pushes the electrons around the wire or whatever it is that the current is passing through. Sometimes it's the battery, sometimes it's an outlet, things like that. Now, actual current in the really real world is the flow of electrons from the negative terminal to the positive terminal of a battery or whatever the voltage source is. Conventional current, which is what engineers use, they pretend that it's actually positive charges that are flowing around from the positive side of the battery to the negative side of the battery. They didn't actually find out that it was electrons flowing until the early 1900s. So that's why it's still used, is because it was used for so long. It doesn't really affect most things, but truly it's electrons flowing. So electrical current is the rate of charge flow, basically. So it's the amount of charge that flows through whatever conducting material there is divided by the time. Okay, the symbol for electric current is I. It's I because I believe it was Franklin coined the term electrical intensity. It was called current later on, and one can imagine that he found that higher currents were more intense than others because they often used their bodies as scientific devices to test things. So he was probably shocking himself and definitely thought that the greater current was more intense. So, but the equation is I equals Q over T, and just like in the last unit, Q refers to charge, so it's the rate of charge flowing. So it's a fairly simple concept. If we think of electrons flowing through a wire, and so basically the faster they flow, the more electrical current there is. Okay. Um, so some ideas of some amperage. Again, current is measured in amps. Um, so 0.001 or 1 milliamp is a little bit of a shock. 5 milliamps starts to hurt at 15.0015 amps. That can override your brain's control of your muscle and start forcing your muscles to contract. A tenth of an amp is likely death, assuming that current's in the right location, and that right location would be around your heart. And what a typical household circuit is way above all of these. It's 15 amps or 20 amps is the typical household circuit breaker. They trip if the current goes above that. So just to kind of give you an idea, not that your house is a death trap by any means, but you do want to be careful with electricity. So a dim light bulb, let's say 40 watt, draws about a third of an amp. How many electrons pass through it in 1 second? Well, a third of an amp means that there's a 1/3 of a coulomb per charge of charge per second. Okay, we know that one electron is equal to 1.60 times 10 to the minus 19th coulombs of charge. So dividing that out, and we get that through that dim light bulb, there's 2.08 times 10 to the 18th electrons per second. So that's a lot of electrons per second. And in 2/3 of an amp, there would be twice that, so 4.16 coulombs or electrons per second. So electric current is simply electrons that is flowing through a conductor. like water flowing through a river, which is why water is often used as an analogy to electricity, because electricity can be somewhat hard to visualize sometimes. So you'll frequently see water used as an analogy. So in a stream, water flows downhill because gravity pulls it down. Okay, and it changes potential energy in the process. It goes from higher potential energy to lower potential energy. If I have two tanks that are connected by a little valve right here, and I remove that valve, okay, the water level will flow from the high tank to the low tank until the tanks equalize out. Okay, it stopped because there was the same amount of pressure on both sides of the connector. Okay, so water stops flowing when there's no pressure difference. In order to keep water flowing, we would need to maintain a difference in height. We'd have to maintain a higher height on one side or the other in order to keep water flowing from one tank to the other. Okay, so in order to do that, we could use a pump. Okay, water could pump water from the lower tank over to the higher tank, and then we would have water continuously flowing. We'd have a continuous current. Okay, in order to keep electrons flowing, we need an electron pump, and a battery sometimes serves as that purpose. Sometimes it's your electrical outlet, although they work a little bit differently, and that's alternating current, which is beyond the scope of this class. Okay. So here we've got electrons flowing from the negative side of the battery to the positive side of the battery, but in general, what we're going to use is conventional current, which would be positive charge flowing from the positive side to the negative side of the battery. Okay, so that's what this shows right here. Here we've got the positive side of the battery. This represents a battery, by the way, a voltaic pile per se. And we see that the charges are flowing from the positive to the negative. They're going through the light bulb, they're not really in this case. So batteries create voltage. Okay, a pump creates pressure that causes water to flow. A battery creates voltage. So that's the second term that's really important. So current was the first one. It was just that idea of charge flowing around a loop. The next important term is voltage, and voltage causes current to flow. Okay, so sometimes it's referred to as electrical potential. Usually it's just called voltage. This one makes pretty much sense. It's the symbol for voltage is a V, and it's measured in volts. So you have a 9-volt battery, and in the equation it's V. So it's pretty much V's all around. A V really stands for a joule per coulomb. So it's a joule of energy per coulomb of charge is what it really stands for. So we'll see it in the equation a little bit more. Okay, the potential energy per coulomb of charge. Okay, some voltages you might see. A lemon battery that you might make that you made maybe in 5th grade might have had about a 0.5 volt. Your AA's, AAA's, C's, and D battery all are 1.5 volts. You'll never guess about a 9-volt battery. Your household current in your outlets is 120 volts. My Van de Graaff generator, the thing up on the shelf that you might have gotten to shock yourself with, or maybe not, that generates about 20,000 volts. Those long distance transmission lines for electrical power and wires can be between 70 and 800,000 volts. And lightning can generate around 100 million volts. So just some ideas of voltage. So the lower we go down in this tube of water, the greater the pressure is. So just like as you go down in a pool of water, your ears start to hurt as you get towards the bottom of a pool. The lower we go down in a tank of water, the greater the pressure there is. Okay, which that greater pressure is going to cause a greater flow rate through the same size hole. If these two holes are identical, we're going to get a greater flow rate out of this one because there's more pressure. Okay, the bigger the voltage, okay, instead of the flow rate of water, we're going to have the greater flow rate of electrons. So we're going to have the greater current. So As voltage increases, current increases too. So we can think of voltage as an electrical pressure. Okay, it's an electrical pressure that pushes electrons around, and it's produced by batteries and among other things. Okay, so the two main ideas of voltage are it's the electrical pressure and it's also the energy, quote unquote, per electron. Really, it's the joules per coulomb. Remember how we said a volt is also known as a joule per coulomb? We can think of it as how much energy the electrons have. Okay, so as electrons lose voltage, they lose energy, and they dump that energy off at some device or something like that. Okay, so energy is electrical pressure, and it's also the quote unquote energy per electron. Okay, so a pump not only creates pressure, it also increases the potential energy of the water. So as it pumps the water up, okay, that pressure gets converted to potential energy, okay, and it flows from higher potential energy down to lower potential energy. Okay, a kilogram of water has more potential energy up here, okay, than it does in the lower tank. Okay, and that pump takes that lower potential energy water and pumps it up to a higher potential energy. Okay, so we can think of it as a certain location has a certain joules per kilogram of water. Okay, joules of energy per kilogram of water, and water naturally flows towards lower potential energy locations. Okay, in order to keep the water flowing, we got to have the pump, which pumps the water back up to higher potential energy so that it can flow back down to lower potential energy. Okay, a battery is like an electron pump, and it pumps the electrons up to higher potential energy. So what this represents the battery here. This is blue. Okay, and it shows that we're taking our positive charges, okay, our pretend positive charges, and we're pumping them up, okay, to a higher potential energy, a higher voltage. Okay, and here they reach a light bulb or something like that, and that's when they flow down towards lower energy and they dump off their energy in the form of light, of a light bulb. And we'll talk about resistance more specifically. It's the resistance of the light bulb that does that. And then they flow back to the battery where they're pumped up again. So we gotta have this battery, this pump, otherwise current stops. Okay, so a charge has a higher potential energy, okay, a higher voltage up here on this side of the green paddle wheel than it does on the lower end. Okay, and electrons naturally flow from higher to lower, just like the water did. Okay. Um, okay. So this is similar to the circuit that you just saw before. So this is the battery, the electron pump, and it's pumping the electrons up. Okay, they're flowing through the wire. Okay, notice that in the wire they didn't lose. This represents the wire, by the way. Okay, this part where the potential energy isn't changing. Okay, we say the electrons don't lose any energy along the wire. So the electrons have a greater potential energy up here. Okay, than when they flow across the light bulb, they dump off that energy, that voltage, and they have a lower energy here. Okay, and then the battery pumps them back up. Okay, if you ever wanted to see what's inside a battery, this is probably an old alkaline battery, and so there's a carbon rod in the middle of it, and then there's a paste of some chemicals that aren't too terribly toxic. I wouldn't eat it though. Wash your hands afterwards. And anyway, it's this chemical reaction inside that happens that gives the electrons their energy. And when you run out of the reactants for that chemical reaction, the battery dies. Okay. AA, C, and D batteries all produce the same voltage because they all have the same chemical reaction that goes on inside. The only difference between a AA or AAA and a D battery, which is of course a big one, is that there's more room for reactants, so they last longer. Okay, before the battery dies. Okay, which sometimes you want a big battery, sometimes you want a small battery. Okay. Now, if we've got two holes at the same depth, meaning the same water pressure. So this is back to a tube of water. Again, we use the water analogy pretty extensively. If I have a skinny hole and I have a more open hole, I'm going to get more water flowing out of the bigger hole. Okay, we would say that the skinnier hole has more resistance to water flow. Okay, it resists the water flowing through it, and the bigger hole has less resistance. Okay, electrical resistance is how much something like a wire resists electrons flowing through it, or positive charge. Okay, I guess I'll switch back and forth between the two, but conventional charge is positive. Real current is electrons. So the symbol for electrical resistance is R, and the symbol for it is not the symbol. I'm sorry. The unit for it is ohms. It's measured in ohms. Okay, and the abbreviation for ohms is this Greek uppercase omega. Okay, so in the equation you'll see it as R, which makes sense. It's R. Okay, and next to a number you will see it typically with this ohm symbol, or written out as ohms. Okay, all right. The two main ideas of resistance is resistance. Okay, resists the flow of electrons. Okay, it tends to reduce the flow of electrons, not going in and out of it at the same time. It doesn't accumulate electrons. Okay, but if you swap out something for a higher resistance, it'll cause the electrons flowing around that loop to go down. Okay, and electrical resistance causes electrons to lose energy. Okay, and again, that's kind of a simplified term, but they're going to lose voltage. They're going to lose electrical potential energy. Okay, all right. So here, back to our little positive charges flowing around a circle. So here we've got the battery pumping the positive charges up with energy and voltage. They flow along the wire. They're not losing any energy or voltage. Okay, and here they're going through the resistor. Okay, the resistance. Okay, and this is the point at which they lose energy, which they lose voltage. Okay. Okay. Now, when I say that resistance reduces the flow of electrons, I'm not saying, if you look at this this resistor paddle wheel right here, that there's any less protons coming out of the paddle wheel as going in. The flow rate of protons going in is the same as the protons flowing out. Okay, I'm not saying that it reduces electrical current like that. What I'm saying is, okay, is if I took out this resistor, okay, that the current would go way up in this loop. Okay, or if I swapped this resistor out for one that had an even higher resistance, that would cause the flow rate everywhere to go down. Okay, that's what I'm trying to say. So now that energy's got to go somewhere, because energy is conserved. So when the electrons or protons, okay, they go through that light bulb, which has a high electrical resistance. Okay, when they do that, they lose voltage, and therefore they lose energy. And that energy gets transferred into heat and light. Okay. Sometimes the electrical resistance is a good thing, like in a light bulb. Sometimes it's a bad thing, depending on what kind of machine we're operating and where it's occurring. Okay. Now, wires have very, very little resistance. And for the sake of our problems, we're going to assume that they have no resistance. So we don't lose any energy along the wires. We have ideal wires. Okay. So that's why we're not losing any elevation along the between the battery and the resistor. It's because we have ideal wires. Okay, so so electrons, they go to the battery, they pick up voltage. So the green watermelons or barrels or whatever represent voltage. Okay, they don't lose any voltage along the way in the wire. They reach the light bulb, and that's when they dump off their voltage. Okay, and now they're coming back to the battery with essentially 0 voltage. Okay, and they get pumped up again with 6 volts of energy, and They dump off their energy, et cetera, et cetera. Okay. All right, and that is it for today. Current, voltage, and resistance main ideas. Hopefully you got a bit of an understanding about that, and we'll talk to you later.